29 days, it vanished behind the Sun. When it reappeared, its path had changed. Astronomers calculated the odds of its new, precise trajectory happening by chance, 1 in 26,000. This wasn't a random journey. It was a calculated move, executed in the one place no one could see. For 29 agonizing days, it was gone, vanished. The object known as 3IATLAS, a third recorded visitor from the void between stars, had slipped behind the Sun, and every telescope on Earth was blind. We could only wait and calculate and hope our predictions held. But they didn't. When it finally emerged from the solar glare, blinking back into our field of view, something fundamental had changed. Its path through the cosmos was different. It had shifted, a minuscule but monumental alteration executed in the one place we couldn't see. A course correction so precise it defies belief. New data now confirms our deepest suspicion. This is not a random journey. 3IATLAS is going somewhere specific, and we have finally calculated its terrifying destination. It is now on a perfect trajectory for Jupiter's Hill sphere, the gravitational boundary where a passing object can become a permanent resident. The odds of this happening by pure chance are a staggering 1 in 26,000. This isn't a lottery ticket, it's a calculated move. And the most chilling part, the most efficient, the most logical time to perform such a maneuver was exactly when it was out of sight, hidden by the Sun moving at its fastest. It's the perfect heist, pulled off in the cosmic blind spot. Astronomer Avi Loeb calls it a mothership deployment. And if he's right, the Jupiter system, the strategic high ground of our solar system, is about to get very, very crowded. What arrives in March of 2026 might not just be a rock, it might be a delivery. And it might be watching back. Before we go any deeper, if you're as captivated by this unfolding mystery as I am, hit that subscribe button. You won't want to miss a single moment of this real-time journey as we track this object toward its fateful rendezvous. Leave a comment. Tell me where in the world you're watching from, what time it is for you right now. I want to feel the global scale of this audience, all of us looking up together. This is part 1, the keyhole revelation, the trajectory we weren't supposed to see. You know that feeling when you catch someone in the middle of an act they thought was entirely private? That split-second flicker in their eyes when they realise they've been seen. We might be having that moment with something not of this Earth. The object we call 3IATLAS isn't just tumbling aimlessly through our neighbourhood. It has a destination, and we've just figured out what it is. The target is the very edge of Jupiter's zone of gravitational dominance, that invisible bubble called the Hill sphere where the giant planet's pull overcomes the Sun's, where a visitor stops being a passerby and can become an occupant, a moon a permanent fixture. This is where the data becomes deeply unsettling. Harvard astronomer Avi Loeb ran the numbers. On March 16, 2026, the radius of Jupiter's Hill sphere will be approximately 53,502 million kilometers. That's the size of the capture zone, the gravitational net. Now, look at what the JPL Horizon system calculated for 3IATLAS. Its closest approach to Jupiter will be 53.445 million kilometers on the exact same date. The difference is a mere 60,000 kilometers. In the scale of the solar system, that isn't a near miss. That is threading a needle from 1 billion miles away. To put that in perspective, imagine standing in New York and throwing a dart blindfolded during a hurricane and having it land perfectly in the bullseye of a dartboard in Los Angeles. That's the level of precision we're witnessing. The calculated probability of this happening randomly is about 1 in 26,000. Those aren't odds. Those are a cause for deep suspicion. This narrow zone, this keyhole, isn't just any patch of space. It's the sweet spot. If you wanted to slip into orbit around Jupiter without using massive amounts of fuel, without announcing your presence with a brilliant rocket burn, this is precisely where you would aim. You drift into the Hill sphere at just the right angle, at just the right speed, and the planet's own gravity does the rest, gently capturing you. It's elegant, efficient, and according to a growing number of voices, it might be exactly what we are seeing unfold in real time. But the most skin-crawling part of all is that 3IATLAS didn't start on this path. When we first spotted it and plotted its course, it wasn't headed for this keyhole. Something changed during that blackout period. During the month it was hidden behind the Sun. Its trajectory was nudged just enough. The shift required what scientists label a non-gravitational acceleration, a tiny push, a whisper of thrust of about 5 ppm 10 7 astronomical units per day squared. It's almost imperceptible, but applied at the right moment when it was moving fastest near the Sun, that tiny push was multiplied by the orbit effect, producing an enormous downstream change in its final destination. And the only efficient window to pull this off, the only time such a small nudge would yield this precise result, was exactly when 3IATLAS was hidden, when no one was watching. Avi Loeb calls this the mothership maneuver, a concept as simple as it is terrifying in its implications. You don't fly your main vessel into the inner solar system where it can be easily spotted. Instead, you aim for the outskirts, for the gravitational fortress of the largest planet, and you set up shop there, deploying whatever you've brought. Probes, sensors, watchers. Then, maybe you leave, or maybe you stay. Parked in an orbit we haven't thought to check carefully. Of course, not everyone agrees. The mainstream scientific response has been measured, cautious. Some researchers argue the precision could be an artifact of refined measurements, that natural outgassing from a comet could just happen to push in the right direction. They caution, rightly, against jumping to conclusions, reminding us that orbital mechanics is complex and coincidences do occur. But these cautious points don't fully explain why the correction happened behind the Sun. They don't explain the timing. They don't explain why the deviation moved the object toward the keyhole rather than away from it. If this is natural, it is the most convenient accident in astronomical history. If it is not, then we're forced to ask very different, very profound questions about intent, capability, and what happens when this object finally arrives. Because if 3IATLAS is heading for Jupiter's gravitational capture zone with this level of precision, it is not arriving empty-handed. Objects do not cross the interstellar void for millions of years just to take a quick look and leave. If something made this journey, if something performed this hidden maneuver, it came here to do something. And Jupiter, with its massive gravity well, its rich system of moons, its commanding position in the outer solar system, would be the perfect staging ground. We're about to find out if we have been looking at a random piece of cosmic rock, or the opening move in a game we didn't even know we were playing. The timeline of the hidden burn is a narrative in itself, a period ripped straight from a heist film where the camera deliberately cuts away, and when it returns the vault is empty and the security guards are none the wiser. For 3IATLAS, that blackout period was its moment in the vault. The chronology is critical. The object reached its perihelion, the closest point to the Sun, around October 30th, 2025. At that moment, it was a relatively close 1.4 astronomical units from the Sun, closer than Mars orbits, but for Earth-based observatories, it was completely obscured, lost in the blinding glare of a billion-watt stellar floodlight. This observational blackout lasted for approximately 29 to 35 days, a period of complete radio silence from a scientific perspective. No tracking, no imaging, no spectral analysis. It flew through the most critical, most dynamic part of its journey, the region where the Sun's gravitational pull is strongest, and the potential for a small thrust to have a massive effect is greatest in utter secrecy. Before it vanished, astronomers had calculated its future path based solely on the predictable tug of gravity. The Sun's pull, the slight perturbations from the planets, all leading to a predictable ballistic trajectory. Standard physics. But when 3IATLAS re-emerged into the observable sky and telescopes locked on once more, it was off. Not by a huge margin, but by enough. Enough that the pristine models no longer matched reality. Enough that the equations had to be revised, forced to accommodate a new, unsettling term, a non-gravitational acceleration. In plain language, this means something pushed on the object besides gravity. For a typical comet, this is outgassing. Ice heating up, vaporizing and jetting away from the surface, the rocket-like thrust of Newton's third law in action. But here is where the plot thickens. The measured non-gravitational acceleration for 3IATLAS was minuscule, yet its direction was anything but random. It wasn't a chaotic push in some arbitrary direction dictated by a random patch of ice heating up on a tumbling irregular surface. The push was aligned, with an almost perfect vector, precisely along the path needed to shift the object from its original course directly onto the new one aimed at Jupiter's keyhole. This is the detail that separates a curious anomaly from a profound mystery. Natural outgassing is messy. Comets are lopsided, they rotate, they heat unevenly. Jets fire in bursts and in different directions, leading to a noisy, wobbling net acceleration. What we see with 3IATLAS is surgically clean, too targeted. The acceleration vector points where it needs to point to achieve the desired outcome. And then there is the timing, the masterstroke of the entire maneuver. The timing aligns perfectly with the observational blackout. If you were an engineer designing a covert course correction for an interstellar probe, this is textbook. You wait until you are hidden behind the one object that blinds every telescope on and around Earth. You apply your thrust when you are moving at your highest velocity near perihelion, because that is when the Oberth effect gives you the biggest change in trajectory for the smallest expenditure of fuel. Orbital mechanics rewards this kind of patience and precision, and whatever corrected 3IATLAS's course demonstrated a masterful understanding of both. It is crucial, however, to pump the brakes and acknowledge the scientific counter-narrative. The broader community of comet scientists is far from sold on this interpretation. They argue, compellingly, that what we are seeing is well within the bounds of natural behaviour for an interstellar object. We have a sample size of 3. We don't know how these strange travellers, forged around other stars, behave. Their composition could be different, their volatile ices could be trapped in unexpected ways, and when they finally feel the heat of a star after eons in the deep freeze, they could release gas in patterns and with a coherence we have never witnessed before. Other researchers suggest the apparent precision could be an artifact of our own modelling process. When you get new data, you refine your orbit, you curve fit, you tweak parameters until the model matches the fresh observations. Perhaps we are overinterpreting the match, and the keyhole alignment is a consequence of how we are processing the measurements, not a reflection of a deliberate physical act. These are legitimate, necessary scientific concerns. We do not have proof of anything artificial. What we have is a pattern, a sequence of events that is profoundly difficult to explain through natural means alone, a pattern that fits an artificial explanation with an almost uncomfortable neatness. There is another piece of evidence that is harder to dismiss. After 3IATLAS emerged from behind the Sun, several observatories managed to capture images that showed distinct jets, visible structures of gas and dust extending from the nucleus. Jets are normal for comets, but Loeb and his colleagues argue that the orientation, the timing, and the strength of these particular jets are consistent with a directed maneuver rather than the chaotic sputtering of random outgassing. They suggest we might be looking at the exhaust plume, the visible signature of whatever propulsion system gave the object its gentle, decisive nudge. Again, this is contested. Other scientists look at the same images and see nothing more than typical cometary activity. Without spectroscopy to analyse the composition of the jets, without a close-up look, we cannot say for sure. But the correlation is stark. The jets appeared right when we would expect them if a burn had occurred, and they appeared precisely when the object's trajectory was confirmed to have shifted. The implication, if we follow this thread to its logical conclusion, is staggering. If 3IATLAS performed a hidden manoeuvre, if it timed that manoeuvre to coincide perfectly with a period of guaranteed invisibility, then this object is not merely drifting, it is navigating, it is executing a plan. And if it is executing a plan, then an intelligence somewhere at some time conceived of that plan, which means we are not alone. And in a more unsettling twist, it suggests we are not the first to arrive at Jupiter. We are the newcomers. To truly grasp the magnitude of what is happening, we must move beyond the simple fact of the trajectory shift and into the realm of probability, into the cold, hard math that screams that this is no accident. The number that haunts this entire mystery is 1 in 26,000. This is the estimated probability that a random interstellar object would, by sheer chance, align itself with the narrow dynamic boundary of Jupiter's gravitational capture zone. To understand why this number is so paralyzing, you must understand what it represents. This isn't about hitting a static target in the vast emptiness of space. It is a 6-dimensional problem of breathtaking complexity. Describing an orbit requires 6 numbers, 3 for your position in space and 3 for your velocity. The keyhole around Jupiter is not a fixed hoop hanging in space. It is a moving, breathing zone that only matters if you approach it at the exact correct speed, from the exact correct angle, at the exact correct time. Arrive too fast and you blow right through the Hill sphere, your trajectory barely bent. Arrive too slow, and you might spiral in or fall back toward the Sun. The margins are razor thin. Jupiter itself orbits the Sun at about 13 kilometers per second. The Hill sphere radius fluctuates, but around the time of 3IATLAS' arrival, it will be about 53.5 million kilometers. Yet the actual keyhole, the specific region within that sphere where you can slip into a stable orbit without a significant burn, is a tiny fraction of that volume. The 60,000 kilometer difference between the predicted Hill sphere radius and the object's closest approach is that margin. On the scale of the solar system, it is a microscopic window, and we must consider the time dimension. Jupiter's Hill sphere is not stationary. It moves with the planet along its 12-year orbit around the Sun. If 3IATLAS arrived a week earlier or a week later, the keyhole would be in a completely different location. The alignment we are witnessing is not just spatial, it is a perfectly timed temporal rendezvous. The object is arriving at the right place at the precise right moment. Some orbital dynamicists understandably argue that the 1 in 26,000 figure might be exaggerated. They point out that as we get more data and refine our observations, the uncertainties shrink, and what initially looked like a wild improbability might become somewhat less improbable. This is a fair and scientific point. Our models are constantly evolving, and today's orbit is more accurate than yesterday's. But here is the powerful counter-argument. Even if refinement makes the final match seem less surprising, it does not explain the direction of the change. The non-gravitational acceleration did not push 3IATLAS in a random direction. It pushed it toward the keyhole. If that tiny thrust had been oriented in any other direction, the object would have missed Jupiter's gravitational net entirely. The fact that the push happened to be aligned with the exact vector needed to hit the target is where the true improbability lies. Think of it like this. You're trying to hit a target in the dark. You fire a shot and miss. Then, as you prepare to fire again, someone randomly nudges your elbow. The odds of that random nudge perfectly correcting your aim and making the bullet strike the bullseye are astronomically lower than the odds of the nudge sending your shot even further off course. That is the essence of what we are seeing. The course correction moved 3IATLAS closer to the target, not further away. This is an active improvement of aim, not a random perturbation. Then there is the sheer size of the parameter space to consider. Orbits exist in a 6-dimensional continuum. For any given starting point outside the solar system, there are effectively an infinite number of trajectories an object could follow. The overwhelming majority of these trajectories do not bring you anywhere near the inner solar system. Of the infinitesimally small fraction that do, most do not pass close to any planet. Of the vanishingly small fraction that pass near a planet, almost none pass through the planet's Hill sphere, and of that absurdly rare fraction, virtually none pass through the exact keyhole where gravitational capture is possible. The keyhole is a needle in a haystack, inside a warehouse full of haystacks, on a planet made of hay. Hitting it requires a precision that simply does not happen by accident. And yet, all the data suggests 3IATLAS is about to do just that. In March of 2026, we will know for sure. The object will either pass through the Hill sphere boundary as predicted, or it will not. If it does, if the match holds with the precision we are currently seeing, we are left with only 2 plausible options. Option 1, we have just witnessed the most spectacular coincidence in the history of modern astronomy. Option 2, we have witnessed something AIM. It is vital to be clear here. Extraordinary claims require extraordinary evidence. The scientific method is built on a foundation of healthy skepticism. We do not get to leap to thrilling conclusions just because they are exciting or terrifying. But by the same token, we cannot dismiss compelling patterns simply because they make us uncomfortable. The data is what it is. The numbers are what they are. And right now the numbers are shouting that something highly unusual is occurring. Critics rightly warn that we are pattern-seeking creatures, wired to find meaning in randomness, to see faces in clouds and conspiracies in coincidence. Perhaps that is all we're doing here, draping a natural phenomenon in a dramatic narrative because the story is more captivating than the mundane reality. That is entirely possible, but it is also possible that sometimes the pattern is real. Sometimes the face in the cloud is an actual face. Sometimes the coincidence is a clue. The profound importance of the 1 in 26,000 number is not that it proves anything conclusively. It does not. What it does is dramatically shift the burden of proof. If the odds are truly that low, then the natural explanation that this is just a random rock that happened to perform a perfect orbital intercept becomes the extraordinary claim. At a certain point, invoking blind chance becomes more far-fetched, more requiring of a leap of faith than invoking intent. We will return to the evidence, but first we must understand why the destination itself matters so much. Because if this is intentional, if something is heading for Jupiter's Hill sphere on purpose, then the question is not just who sent it, the question is why Jupiter? And the answer to that question changes everything about our place in the cosmos. If you were an advanced civilization looking to establish a quiet, persistent and strategic foothold in a new solar system, where would you go? The obvious anthropocentric answer is Earth. It is the planet teeming with life, with activity, with the radio signals and city lights that scream, "Here we are!" But if you think strategically, if you plan for the long term, Earth is arguably the worst possible choice. Earth is loud. It is crowded with sensors, satellites, and billions of curious, technologically adept humans who would immediately notice anything out of the ordinary. It is the last place you would go if your primary objectives were discretion, observation, and long-term stability. Jupiter, on the other hand, is perfect. Let us walk through the reasons why the gas giant is the real prize in our solar system. First, there is the sheer, overwhelming fact of its gravitational dominance. Jupiter's mass is 318 times that of Earth. Its Hill sphere, that zone of gravitational influence, is enormous, extending over 50 million kilometers at its widest. Everything inside that bubble is, for all practical purposes, Jupiter's territory. The Sun's gravity is still a factor, but Jupiter wins. If you release an object inside the Hill sphere with a low enough relative velocity, it stays. It does not need engines firing, it does not need fuel. Gravity itself does the work, tethering it to the planet for eons. This is the ultimate in energy-efficient parking. Second, there is the Moon system, a miniature solar system in its own right. Jupiter has at least 79 confirmed moons, with likely dozens more awaiting discovery. Among them are worlds that rival planets. Ganymede is larger than the planet Mercury. Europa is believed to harbour a vast global subsurface ocean containing more liquid water than all of Earth's oceans combined, a potential haven for life. Io is the most volcanically active body in the entire solar system, its surface constantly remade by fiery eruptions. Callisto, ancient and heavily cratered, offers a stable geologic record dating back billions of years. These are not mere rocks, they are worlds, rich with resources, and they orbit in a complex stable system that has been running like clockwork for billions of years. If you wanted infrastructure, raw materials, or simply places to hide, Jupiter's moons are a veritable gold mine. Third, there is the magnetosphere. Jupiter's magnetic field is the most powerful of any planet, a ferocious dynamo about 20,000 times stronger than Earth's. It stretches for millions of kilometers in every direction, trapping charged particles and generating intense, deadly radiation belts. For humans, this radiation is a lethal barrier, but for machines, for probes engineered to withstand harsh environments, it is a non-issue. In fact, the magnetosphere itself could be a tremendous asset. It is a natural particle accelerator, a colossal energy source if you possess the technology to tap it, and a perfect natural cloak for any low-level emissions your own equipment might produce. Fourth, and perhaps most critically, there is the strategic position. Jupiter sits like a colossal fortress at the boundary between the inner and outer solar system. From its vantage point, you have a commanding view of everything. You can monitor the asteroid belt, watch Mars, keep a constant eye on Earth, all while remaining far enough out that you're not in the direct daily scrutiny of the inner planets. It is the ultimate high ground. In military strategy, controlling the high ground wins wars. In cosmic terms, controlling Jupiter wins the solar system. Now, let us talk specifically about the Hill sphere boundary itself. Why aim for the edge? Why not dive straight into a tight orbit around Jupiter? Because the edge is where the orbital mechanics work most elegantly in your favour. At the boundary of the Hill sphere, Jupiter's gravitational influence is just strong enough to hold onto objects, but the escape velocity, the speed needed to break free, is relatively low. Avi Loeb calculated that at a distance of about 53.5 million kilometers, the escape velocity is a mere 2.2 kilometers per second. On a cosmic scale, that is walking speed. What this means is profound. If you arrive at the edge of the Hill sphere and wish to deploy probes, you barely need to slow them down. A tiny nudge, a whisper of a burn, and they are captured. They will not fall back into interstellar space, nor will they crash into Jupiter. They will simply drift into stable orbits, held effortlessly by the planet's gravity, waiting, watching, and listening. And this leads to the most terrifying part of the entire strategy. Once you're in orbit around Jupiter, once you're tucked safely inside the Hill sphere, you're almost impossible to detect from Earth. We struggle to find and track asteroids in our own immediate neighbourhood. Finding small dark objects in the chaotic orbital space of Jupiter, amidst its swarms of moons, its Trojan asteroid clouds, and its rings of dust, is like trying to find a specific needle in a factory that manufactures nothing but needles. Unless an object deliberately gives off a strong signal or reflects a significant amount of sunlight, it is effectively invisible. This is the core logic behind the mothership hypothesis. The term sounds like science fiction, but it is deeply descriptive. A mothership is not meant to stay on the front lines. It is a delivery vehicle. It carries a payload across a vast distance and deposits that payload at a strategic location. Then, its primary mission complete, it either leaves or retires to a quiet, parking orbit. The payload, the probes, the sensors are the ones that do the actual work. They are the silent watchers, the data gatherers. If this is what is happening with 3IATLAS, if it drops off a cluster of small autonomous probes into Jupiter's Hill sphere in March 2026, we might never see them. Not unless we are looking with exquisite care, and not unless we know exactly what to look for. A probe the size of a car would be indistinguishable from a small captured asteroid. A probe the size of a person would be utterly beyond our current detection capabilities. You might wonder, if Jupiter is such a perfect strategic location, why haven't we seen any evidence of previous visitors? Why aren't there already strange artifacts in orbit or on the moons? The answer is hauntingly simple. Maybe there are. We have only been seriously studying the Jovian system for a few decades. NASA's Juno probe arrived in 2016. Before that, the Galileo spacecraft orbited from 1995 to 2003. Before that, we had only brief flybys, quick, snapshot glimpses. We have barely begun to catalogue the millions of objects in Jupiter's gravitational domain. There could be dozens, even hundreds, of artificial objects in unusual orbits that we have casually written off as natural captured asteroids or debris from ancient moon-moon collisions. We do not know what we are looking for, so we do not see it. But if 3IATLAS arrives in March 2026 and something changes, if new, unexplained objects suddenly appear in the orbits around Jupiter, if the delicate ballet of the moons shows minute perturbations, if there is any sign that the Jovian system has just become more crowded, then we will have our answer. We will know that Earth was never the primary target. We were just the interesting neighbours. Jupiter was always the prize, and if someone or something has already claimed it, if they are already there waiting, then the question becomes not what are they, but what do they want with us? Are we being studied like animals in a reserve? Are we being ignored as inconsequential? Or are we a part of a plan so vast we cannot yet comprehend our role? The clock is ticking down to March 2026, and when the moment arrives, we will finally learn whether Jupiter's Hill sphere is the empty frontier we believe it to be, or if it has been occupied territory all along. We are not sending a dedicated mission to watch this unfold. We do not need to. There is already a sentinel at Jupiter. Right now, as you process these words, NASA's Juno spacecraft is tracing its long, looping orbits around the gas giant, diving perilously close to the cloud tops before soaring out into the depths of the radiation belts. Juno launched in 2011 and arrived at Jupiter in July 2016 on a mission designed to peer beneath the planet's swirling clouds, to map its monstrous magnetic field, and to unravel the secrets of its formation and interior. It has sent back breathtaking images of polar cyclones, data on a potentially fuzzy core, and insights into the auroras that dance at its poles. But in March of 2026, Juno might bear witness to something its engineers never imagined, an event that could redefine its mission entirely. Juno's orbit is highly elliptical. Its closest approach, Peryov, takes it within a few thousand kilometers of the planet's atmosphere. Its farthest point, Apogee, carries it millions of kilometers away. Each full orbit takes about 53 days. This means that roughly every 2 months, Juno gets an intense close-up view of Jupiter and its immediate vicinity, while the rest of the time it is a lonely traveller in the outer magnetosphere. The spacecraft is equipped with a powerful suite of instruments: JunoCam, a visible light camera that has provided stunning public images; GIRAM, the Jovian infrared auroral mapper that sees in heat; the WAVES instrument, which listens for radio and plasma waves; sophisticated magnetometers, particle detectors, and precision gravity sensors. None of these instruments were designed to look for alien probes. Juno's mission is pure planetary science, not SETI. But these tools are incredibly sensitive. If something unusual occurs in Jupiter's vicinity, a sudden, unexpected glint of reflected sunlight, a burst of anomalous radio signals, a cluster of warm objects against the cold background of space, Juno could, in theory, detect it. Whether anyone on Earth notices depends entirely on whether anyone is specifically looking for it. Let us envision the scenarios if the mothership hypothesis proves correct. Scenario 1. 3IATLAS passes through the Hill sphere boundary in mid-March 2026, and, as it does, it releases a cloud of smaller objects. These probes, perhaps only a few meters across, use minimal low-signature propulsion to insert themselves into stable, long-term orbits around Jupiter. From Earth, they would be invisible. But Juno, if its orbit happens to place it in the right position at the right time, might catch a fleeting reflection, a brief, unexplained flash of light in its imaging data, a transient signal that appears for a few frames and then is gone forever. Scenario 2. The deployed probes are designed for stealth. They are coated in ultra-dark, non-reflective material, but they still emit heat. Every object warmer than absolute zero radiates in the infrared. GIRAM, Juno's infrared instrument, could potentially detect a cluster of unexplained warm spots against the profound cold of space. Again, this is a matter of fortuitous timing and pointing. If Juno is looking the wrong way, or if the probes are too cool or too small, we would miss the signature completely. Scenario 3. The probes are not entirely passive. Perhaps they need to communicate with each other to form a mesh network, or perhaps they send a brief data burst back toward the departing 3IATLAS, or out into interstellar space. The WAVES instrument is designed to pick up the complex radio emissions from Jupiter's magnetosphere. A structured, modulated signal, a burst on an unexpected frequency that does not match any known natural phenomenon, would stand out like a scream in a library. This is the scenario where detection becomes most likely, but it is also the scenario where the probes would be either momentarily careless or unconcerned about being detected. Scenario 4, the null hypothesis favoured by most of the scientific establishment, nothing happens. 3IATLAS passes through the Hill sphere, continues on its way, and sails out into the outer solar system never to be seen again. No deployment, no probes, no drama. It was, despite all the intriguing oddities, just a rock after all. The mothership hypothesis collapses, but if this is the outcome, it raises its own perplexing questions. Why did it perform that precise hidden maneuver? Why did it aim for the keyhole with such astonishing accuracy if it had no intention of using it? The central problem with all these scenarios is that we are largely relying on luck. Juno is not a watchdog. It is a specialized scientist focused on Jupiter itself. Its instruments have limited fields of view, and its orbit is predetermined. If a deployment event occurs outside its immediate line of sight, or if the timing is off by even a few hours, we could miss the entire event. And even if Juno does capture something anomalous, the data takes time to get to Earth. The spacecraft is nearly 800 million kilometers away. Signals traveling at the speed of light take over 40 minutes one way. We will not know what Juno saw until long after it has seen it. There is also the human and bureaucratic element. If Juno's data stream contains an anomaly, would it be flagged immediately? Would an alert mission controller recognize it and escalate it? Or would it sit in a vast queue of routine data, waiting for weeks or months to be processed by scientists who are primarily looking for storms and magnetic field interactions? Space missions generate a torrent of data, and most of it is by design mundane. Finding the one unexpected needle in that haystack requires you to be actively looking for a needle, and right now the teams analysing Juno data are understandably looking for the hay. But let us assume the best case scenario. Let us assume that between now and March 2026, the predictions around 3IATLAS gain enough traction that the astronomy community prepares a coordinated watch. Telescopes around the world and in space are pointed at Jupiter. The Juno mission team is briefed and they adjust the spacecraft's observation schedule to maximize coverage during the critical window, we are for the first time truly looking. What then? If we detect even a single, unambiguous artificial object, if we find something in orbit around Jupiter that cannot be explained by natural processes, the implications are immediate and world-altering. It means we are not alone. It means another intelligence possesses technology capable of interstellar travel and precise orbital deployment. It means Earth is no longer the only technologically active world, and we're almost certainly not the most advanced. It means our solar system is, at least in part, already someone else's domain. And it means we, as a species, must instantly grapple with what comes next. Do we attempt to communicate? Do we observe from a terrified distance? Do we begin to prepare for realities we have only ever explored in fiction? Conversely, if we detect nothing, if Juno and every telescope on Earth see no evidence of any deployment, we are left in a state of profound uncertainty. Did nothing happen? Or did something happen that was so stealthy, so technologically sophisticated that it slipped past all our sensors? Did the probes deploy and immediately go dark? Did 3IATLAS change its mind? Or was the entire thrilling, terrifying narrative simply a case of humans seeing patterns in the random noise of the cosmos? March 2026 is the deadline. The surveillance window is narrow. If something is going to happen, it will happen then. And when it does, Juno will be our closest witness, a silent robotic eye already on the scene. Whether we are prepared to believe what it shows us is a question that lies not in the realm of astronomy, but in the heart of human nature itself. The pieces are on the board, the object is approaching, the witness is in place. All we can do now is wait and watch. But as we wait, we are compelled to ask deeper, more fundamental questions about the nature of the object itself, about how such a journey could even be possible, and about what its existence implies for the universe we thought we knew. To comprehend what 3IATLAS might be, we must step back and think like an engineer tasked with a project of literally astronomical proportions. Imagine you need to send a physical payload across the light years to another star system. Not a radio signal, but something tangible, a probe, a suite of instruments, perhaps a replicator. Your target is a system you have identified as interesting, perhaps because it has planets, perhaps because it has signs of life. You want to know what is there, but you cannot go yourself. The distances are too vast, the timescales too long for any biological being. So, you build a vessel that can make the trip autonomously. Forget the sleek starships of science fiction. Think in terms of brutal, unforgiving physics. The speed of light is an iron law. You are not breaking it. This means your travel time is measured in centuries, at a bare minimum more likely in millennia. If your destination is just 10 light years away, and you are travelling at 1% of light speed, a velocity that itself requires staggering energy, the journey still takes 1,000 years. You need a vessel that can survive a millennium in the void, with no repairs, no resupply, just relentless endurance. Second, the problem of energy. Moving mass requires energy, and the faster you go, the more you need. But you cannot carry all your fuel with you like a chemical rocket. The fuel itself has mass, requiring more fuel to accelerate it, leading to a suicidal spiral. So, you must use something else. Solar sails pushed by starlight, magnetic sails that drag against the interstellar medium, perhaps beamed propulsion. Where your home civilization fires a powerful laser or particle beam at a sail on your vessel, accelerating you for years until you are beyond range. Then you coast for centuries, and as you approach your target star, you flip your sail and use its light to slow down. It is a game of patience, not speed. Third, and critically, detection. If you're entering someone else's backyard, you probably do not want to announce your presence with a brilliant rocket plume or a shiny metallic hull. Stealth is a valuable asset, so you design your vessel to be a master of disguise. You coat its exterior in a layer of ice, carbon, and accumulated interstellar dust. You let it tumble erratically. You ensure its albedo, its reflectivity, matches that of a common comet or asteroid. By the time it arrives in the inner solar system, it is virtually indistinguishable from a natural object, and when it gets close to the star, the outer layer of ice heats up and sublimates, producing the classic coma and tail of a comet. It is the perfect camouflage. But beneath this naturalistic shell lies the truth. Structure, machinery, a sophisticated computer brain, and a payload waiting to be deployed. The non-gravitational acceleration we detected could be the result of this camouflaged shell outgassing, or it could be the carefully timed burst of a low-thrust propulsion system, deliberately designed to mimic the look of outgassing. If you time your burn to coincide with perihelion, when natural comets are most active, the camouflage is perfect. The jets we observed could be simple venting, or they could be the exhaust of a purpose-built engine. Without a close-up inspection, the difference is academic. And who is going to fund a multi-billion-dollar mission to intercept and inspect what everyone believes is just another comet? This is where the trajectory becomes the ultimate giveaway. A natural comet does not aim for the keyhole of a gas giant's Hill sphere. It does not execute a precision orbital maneuver while hidden behind the sun, but a mothership does. Because the Hill sphere is the deployment zone, you arrive at the boundary with minimal relative velocity. You release your payload of probes. Each one makes a tiny, almost undetectable burn, just enough to settle into a stable, long-term orbit. Then, the mothership itself, its primary mission accomplished, has choices. It can continue on its way, exiting the solar system to perhaps report back or travel to another star. Or it can itself park in a distant, stable orbit around the Sun, in the Kuiper Belt or the Oort cloud, where it is unlikely to be found for millennia, a silent sleeper agent waiting for a trigger. The probes are the heart of the mission. They are small, efficient, and autonomous. They need no life support. They have no need to ever go home. They are designed to operate for decades, centuries, perhaps even longer, powered by radioactive decay or tiny nuclear reactors. They watch, they listen, they collect data on the planets, the star, the asteroid belt, and especially on the one planet that is unmistakably alive, Earth. Maybe they communicate with each other via tight beam lasers, forming a stealthy mesh network. Maybe they store all data locally, waiting for a future retrieval mission. Or maybe they periodically transmit their findings back to the mothership, which acts as a data mule, or directly out into interstellar space along a predetermined vector. Now, let us consider the propulsion that would make this possible. Rocket engines are out, the fuel mass is prohibitive. Ion drives are better, but still require too much propellant for a millennia-long journey. The feasible technologies are those that do not require carrying your reaction mass. A magnetic sail, or magsail, is a leading candidate, a vast superconducting loop that generates a magnetic field, which then pushes against the charged particles of the interstellar medium. It is slow, constant acceleration, but over centuries it can reach significant speeds. A light sail, as mentioned, is another. The measured acceleration of 3IATLAS, that tiny 5·10⁷ Order 2, fits perfectly within the performance envelope of these technologies. It is small enough to be subtle, to be mistaken for natural phenomena, but large enough that, when applied at the right moment near the Sun, the Oberth effect amplifies it into a course-altering nudge. But this model leads to an uncomfortable temporal perspective. If 3IATLAS is a mothership, it has been travelling for a very, very long time. The nearest star system, Proxima Centauri, is over 4 light-years away. Travelling at 1% of light speed, the journey would take more than 400 years. If it came from further away, we're talking thousands of years. This raises profound questions about the builders. Are they still there? Did they launch this vessel and then, in the intervening centuries or millennia, succumb to war, plague, or simple entropy? Or are they out there now, a thriving civilization patiently waiting for the data stream from their scout to finally light up? And if they are waiting, what is their next move when 3IATLAS reports a successful deployment? Do they send a follow-up mission? Do they come themselves? Or do they simply file the report in a galactic database and move on? There is another, even more speculative possibility. 3IATLAS is not the only one. Perhaps our solar system is being visited by dozens, even hundreds of such motherships, each targeting a different strategic location: Saturn, Uranus, the asteroid belt. Perhaps Earth already has such probes in orbit, objects we have catalogued as natural asteroids like Cruithne or 2016 H03. We have only had the technology to detect small, dark objects for a blink of an eye in cosmic terms. How many have we missed? Critics of the mothership hypothesis rightly point out the total lack of direct evidence for artificial structure. No unnatural metals have been detected in its spectrum, no geometric shapes in its light curve, no structured radio signals. Everything observed can be explained, with some effort, through natural processes, and they are correct. We have no proof. What we have is a pattern of behaviour, a set of characteristics that align perfectly with what a competent interstellar engineer would design. That does not prove intent, but it makes the hypothesis impossible to dismiss. The simplest explanation, Occam's razor, is traditionally taken to be the natural one. But is it truly simpler to invoke a series of breathtaking coincidences, the hidden timing, the precise vector of the nudge, the 1 in 26,000 keyhole alignment, than to invoke a single cause, design? From an engineering perspective, every choice 3IATLAS has made is logical, optimal, and strategic. The final, and perhaps most unanswerable piece of the mothership puzzle is the why. Why would anyone send probes here? What does our solar system possess that is worth a journey of millennia? The most compelling answer is life. Earth is a beacon. From light years away, a sophisticated telescope could analyse the light passing through our atmosphere and detect the unmistakable chemical fingerprints of biology, oxygen, methane, and other gases in disequilibrium. If you are a civilization curious about life in the universe, Earth is a prime target. And if you want to study that life without contaminating it or causing panic, Jupiter is the perfect secluded observatory. But maybe it is not about life at all. Maybe it is about real estate and resources. The asteroid belt is rich in metals. The moons of Jupiter and Saturn are rich in water ice and organic molecules. The Kuiper belt is a vast reservoir of primordial material. A spacefaring civilization might see our system not as a zoo, but as a mine, and they are simply staking a claim before the native species becomes capable of doing so itself. Or perhaps it is purely strategic. Our solar system might lie along a galactic shipping lane, a convenient stopover between more important destinations. Maybe we are just being catalogued, our star and its planets added to a grand atlas of the galaxy. The terrifying and humbling truth is, we are in no position to know. We cannot know without more data. And that is what makes March 2026 the most critical moment in our species' history. If the mothership hypothesis is correct, if a deployment occurs, we will see evidence. It may be subtle, it may be circumstantial, but it will be there. And that evidence will force upon us the biggest questions we have ever faced. Who is out there? What do they want? And are we, in our nascent technological infancy, ready for the answer? In the typical life cycle of a comet, the story reaches its climax at perihelion. The object swings around the sun, puts on its brightest show, and then begins its long, fading journey back into the darkness. We take our final measurements, update our catalogues, and move on to the next discovery. But with 3IATLAS, the October 2025 perihelion was not the climax, it was the prelude. The real event, the moment of truth, is scheduled for months later, in March of 2026. And the more one contemplates this specific timing, the stranger and more significant it seems, hinting at layers of planning that extend far beyond simple orbital mechanics. Let us start with the conditions at Jupiter itself in March 2026. The giant planet is a dynamic, complex system. Its magnetosphere fluctuates in intensity. Its radiation belts swell and recede. The planet's axial tilt, slight as it is, introduces seasonal variations in how it interacts with the solar wind. If you were an engineer deploying sensitive probes into the Jovian environment, you would not do it randomly. You would choose a window when conditions are most favourable, when radiation levels are at a manageable low, when the magnetosphere is in a stable configuration, when the orbital geometries of the moons are optimal for your sensors. We do not yet know if March 2026 represents a special alignment in Jupiter's complex cycles, but the possibility is there, a hidden variable in the equation that we are only beginning to understand. Then there is the Sun. Our star follows an 11-year cycle of activity, from a quiet solar minimum to a turbulent solar maximum. The years 2025 and 2026 place us near the peak of solar cycle 25, a period of heightened solar activity. This means more solar flares, more coronal mass ejections, more radiation flooding the solar system. On the surface, this seems like a terrible time to deploy delicate electronic equipment. More radiation means more risk of damage, more shielding required, but there is another side to this coin. Our active sun creates a noisy environment. The background levels of radio emission are higher, the solar wind is more chaotic, and the entire heliosphere is more turbulent. If your primary objective is stealth, deploying your probes during a period of high solar noise is a masterstroke. Your own low-power communications, your thruster plumes, any minor thermal signatures, all of it gets lost in the roaring static of the star. You hide not by being silent, but by speaking in a crowded, shouting room. Zooming out further, we must consider the heliosphere itself, the giant bubble of solar wind that defines the Sun's domain. Recent data, which we will delve into later, indicates that this boundary is not static. It is changing, shrinking in some directions, becoming asymmetrical. The shape and size of the heliosphere determine how interstellar objects enter our system, how much drag they experience, and how their trajectories are bent. An object navigating from interstellar space would have to account for these factors. Perhaps 3IATLAS is arriving now because the current configuration of the heliosphere presents a particularly easy entry point, a soft spot in our defensive bubble that makes the precise Jupiter intercept maneuver simpler and more fuel efficient. But let us zoom out to the most provocative scale of all, humanity's own timeline. The year 2026 finds us in the midst of a dramatic space renaissance. Commercial spaceflight is a burgeoning industry. NASA's Artemis program is aiming to return humans to the Moon. SpaceX is developing Starship with the explicit goal of reaching Mars. China is building a lunar base. Multiple nations are launching probes to the Moon, Mars and asteroids. Compared to just 2 decades ago, our presence in space is louder, more active and more technologically advanced. We are making our first tentative steps toward becoming a multi-planet species. If you are an outside observer who has been monitoring this pale blue dot for a while, this is the moment you would sit up and take notice. This is the transition from a curious, isolated biosphere to a potentially spacefaring civilization. It is the critical juncture where we stop being merely interesting and start becoming a variable that needs to be assessed, tracked, and perhaps managed. The timing of 3IATLAS's arrival could be a direct response to this uptick in our activity. It is the galactic equivalent of sending a scout to a region that has suddenly become geopolitically interesting. There is a darker, more unsettling implication here as well. If the timing's deliberate, if this arrival is a response to our own expansion, then the mission might not be one of passive observation alone. It could be about preparation. Preparation for what? Open communication? A warning? Or something less benign, like containment or resource preemption? We have no way of knowing, but the coincidence of our coming of age in space with the arrival of an interstellar object performing a precision maneuver is deeply provocative. Of course, the null hypothesis remains the most likely from a conservative standpoint. The timing is pure orbital mechanics. 3IATLAS left its point of origin thousands of years ago, and its arrival now during our specific technological epoch is nothing more than a cosmic coincidence. The universe is indifferent to our timelines. Comets do not schedule their arrivals around human history. But if this is not a comet, if it is a probe, then the timing becomes a variable that can be controlled. And deliberate timing implies awareness. It implies that someone has been watching us long enough to know not just where we are, but when we are. They knew that by the time their probe arrived, we would be at this specific stage of our development. The level of foresight and patience that this implies is staggering, almost incomprehensible to our short-lived, impatient species. They launched a mission that would take centuries to complete, trusting that the data it would eventually send back would be relevant. The alternative is that it is all a magnificent series of chances. 3IATLAS is natural. It wandered in. The precision is a mirage. The timing is luck. It is all just a story we are telling ourselves because the truth is too random, too indifferent. But the more these coincidences stack, the hidden maneuver, the keyhole precision, the arrival during our space age, the more the weight of chance becomes difficult to bear. Between now and March, we need to be watching everything, not just Jupiter. The Sun's activity, the solar wind, the boundaries of the heliosphere, the background cosmic ray flux. If this moment is as significant as the data suggests, there will be ripples, anomalies, patterns in the noise. And if we are truly unlucky, we will see more than just ripples. We will see action. Because if Jupiter is the high ground, the strategic prize of the solar system, then whoever controls it first holds an insurmountable advantage. And as of now, we are not even in the race. The concept of the high ground is one of the oldest and most fundamental principles of military strategy. On a battlefield, controlling the elevated position grants you visibility, range, and a defensive advantage. You can see your enemy coming, and you can dictate the terms of any engagement. In the vacuum of space, the high ground is not about altitude, it is about gravity wells. And in our solar system, Jupiter is the ultimate high ground, a gravitational fortress from which one could theoretically project power and observation across the entire system. Let us explore the chilling logic of this strategy. Jupiter's mass is not just large, it is dominant. It is 2.5 times the mass of all the other planets in the solar system combined. This immense gravity means it controls its orbital neighbourhood with an iron fist. Asteroids are captured into its Trojan swarms, comets are violently flung into new trajectories or ripped apart. Its Hill sphere is a domain tens of millions of kilometres wide. If you wanted to establish control over the solar system, you would not start with Earth, a small, rocky world with a puny gravitational pull. You would start with Jupiter, because from its gravitational throne, you can reach anywhere. Jupiter's gravity well is a natural catapult. Using clever orbital mechanics, you can slingshot probes from Jupiter to any destination in the inner or outer solar system with minimal fuel. Want to send a mission to Saturn? Use Jupiter. Want to drop a sensor into the asteroid belt? Use Jupiter. Want to send a package to Earth? Jupiter provides the kinetic energy. It is the grand central station of the solar system, and all other destinations are just stops along the line. Now, consider the infrastructure Jupiter provides. Its collection of moons is not just a set of rocks, it is a fully stocked toolkit. Io, with its relentless volcanic activity, is a powerhouse of geothermal energy and a source of sulfur and other volatile elements. Europa, with its hidden global ocean, is a potential source of water, which can be split into hydrogen and oxygen for rocket fuel or life support. Ganymede, with its own magnetic field and vast tracts of water ice, is a potential site for a massive base, protected from some radiation and rich in construction materials. Callisto, geologically stable and less irradiated, is an ideal location for long-term storage or sensitive instrumentation. If you are an advanced civilization capable of in-situ resource utilization, you do not need to bring your factory with you. You build it on site using the abundant raw materials Jupiter's moons provide. You bootstrap an entire industrial ecosystem without ever needing to ship a single gram of material from your homeworld. Then there is the magnetosphere itself. While deadly to biological life, Jupiter's radiation belts are a torrent of energy. A civilization that has mastered harnessing such forces could tap this endless stream of high-energy particles for power, for communication, or, if necessary, for defense. The magnetic field could be used to accelerate projectiles, to create powerful jamming fields, or to shield your own activities from prying eyes. It is a ready-made, planet-sized engine. From a surveillance perspective, Jupiter's position is unassailable. You are far enough from the Sun that its glare does not interfere with your observations of the inner planets. You have a stable, predictable platform. Your line of sight encompasses Mercury, Venus, Earth, and Mars. You can monitor all our communications, track every rocket launch, observe our technological development in real time, and we would be virtually blind to your presence. We point our most powerful telescopes at distant galaxies. We rarely conduct detailed, continuous surveillance of the space around Jupiter. And then there are the Trojan asteroids, two vast swarms of objects sharing Jupiter's orbit, one leading and one trailing the planet. These are among the most stable orbits in the solar system. The Trojans are dark, numerous, and poorly catalogued. They are the perfect place to hide. You could place data relays, sensor nodes, or even entire dormant probes among the thousands of known Trojans, and we would never spot them. They would be just more dots of light in a crowded field. Now, let us synthesize this into a strategic whole. Imagine you are a spacefaring intelligence. You have identified Earth as a planet with a developing technological civilization. You are curious, perhaps cautious. You want to observe, to assess, to understand. You do not want to land and cause a panic, and you certainly do not want to reveal yourself until you are ready. So, you set up a surveillance network. Where do you put it? You put it at Jupiter. You send a mothership like 3IATLAS. It arrives at the edge of the Hill sphere and releases a constellation of small, smart, autonomous probes. These probes disperse, using minimal propulsion to enter a variety of orbits, some around Jupiter itself, some around the key moons, some hidden among the Trojan asteroids. They form a mesh network, communicating with each other via tight beam lasers that are impossible to intercept from Earth. They watch, they listen, they record everything: our television broadcasts, our military radar, our internet traffic beamed to satellites, our deep space missions. They store this data, perhaps for decades, perhaps for centuries. They are patient because they are machines. From our perspective on Earth, this network is invisible. The probes are too small, too dark, and too lost in the background clutter of the Jovian system. We would need to be actively looking for them with the right tools, and even then, it would be a monumental challenge. But it is not just about watching, it is about control. If you control Jupiter, you control the gateway to the outer solar system. Any future human mission to the moons of Saturn, to the Kuiper Belt, or to the stars themselves will have to pass through your domain. You will see them coming years in advance, and if the situation ever turns hostile, if humanity somehow becomes a threat, the high ground offers devastating options. You could use Jupiter's gravity to redirect a small asteroid toward Earth. You could use the energy of the magnetosphere to disable our satellites or scramble our global communications. You hold the ultimate strategic advantage. The most terrifying part of this logic is that it is so obvious. Any civilization that has mastered interstellar travel would inevitably see the strategic value of the largest planet in a system, which means if visitors have come before, if they are out there, Jupiter is exactly where they would be. And if they are already there, we are not just late to the game, we may be living in a solar system that is already claimed, and we are the tenants who do not even know who the landlord is. The counter-argument, of course, is the Fermi paradox's classic question. If they are here, why haven't they made contact? The high ground strategy provides a plausible answer, because they do not need to. We are not a threat, merely a subject of study. They are following a protocol of non-interference, or perhaps a protocol of maximum information gathering before any decision is made. Or perhaps they have tried to communicate and we have not recognized the message, mistaking it for a pulsar or some other natural phenomenon. Or maybe, just maybe, Jupiter is empty and we are projecting our own strategic fears onto a dead moon. But we are about to find out. If 3IATLAS deploys its payload in March, if the Jovian system awakens with new artificial activity, we will have our answer. The high ground will be occupied, and humanity will be faced with the most profound existential decision it has ever confronted. In an era of instant communication and open data archives, silence can be louder than any announcement. It is the absence of information where information should logically exist, the gaps in the data stream that breed the most intense speculation. With the story of 3IATLAS, these gaps are not just theoretical, they are central to the mystery. There is the primary 29 to 35 day blackout period during solar conjunction, a gap with legitimate astronomical explanations. But there are other, more subtle silences that have begun to fuel a different kind of narrative, one that lives in the shadowy space between cautious science and outright conspiracy. The fact is, during that critical period when 3IATLAS was nearest the Sun and performing its maneuver, the publicly available data is sparse to non-existent. A handful of astrometric data points, but no continuous imagery, no high-resolution spectroscopy. The official reason is sound. Observing an object that close to the Sun is phenomenally difficult. Ground-based telescopes are blinded. Space-based observatories like SOHO or Stereo have coronagraphs that block the solar disk, but their fields of view are limited. If 3IATLAS did not pass directly through these narrow windows, we would not see it. The gap could be entirely due to bad luck and orbital geometry. But it is also possible, and this is what fuels the conspiracy theories, that observations do exist and have not been released. Space agencies, for entirely legitimate reasons, do not publish data in real time. It goes through pipelines of calibration, processing, and analysis. This can take months. Furthermore, the line between civilian science and national security is incredibly blurry in space. The United States Space Force and its counterparts in other nations operate classified satellites with powerful sensors. If any of these assets detected something unusual about 3IATLAS, something that clearly indicated non-natural properties, that information would almost certainly be classified and sequestered from the public domain, at least initially. Then there are the fringe claims, the rumours that circulate on online forums and are occasionally picked up by tabloid media. They are unverified and unverifiable, but they contribute to the atmosphere of tension. One persistent rumour claims that spectroscopic analysis of 3IATLAS, conducted by an unnamed team at a major observatory, detected the signature of refined metal alloys, combinations of elements that do not occur naturally and require industrial high-temperature processes. Mainstream scientists have universally debunked this, stating no credible evidence exists, but the rumour will not die. Another claim suggests that Juno has already detected unexplained objects in the Jovian system, small, fast-moving targets that do not correspond to any known moons or asteroids. Again, NASA's public statements are clear. Everything Juno has seen is consistent with natural phenomena, but conspiracy theorists point to delays in the public release of Juno's image batches, to periods of instrument calibration that seem to coincide with key orbital events, and they ask the simple, unsettling question: what if we are not being told the whole story? There is also the issue of fragmented international response. Multiple countries tracked 3IATLAS: China, Russia, the European Space Agency, India. All have space agencies with capable telescopes. There is no single, unified, real-time database where all these observations are compiled. Data is released on different schedules, analysed by different teams using different models. This lack of coordination can look, from the outside, like secrecy or even confusion at the highest levels. Let us play devil's advocate for a moment. Suppose a space agency or a military organisation did obtain clear and convincing evidence that 3IATLAS is artificial. What would they do? Would they hold a press conference immediately? Almost certainly not. The protocol for such a world-shattering discovery is not established. They would likely move to verify, and verify again. They would convene closed-door meetings with top scientists, political leaders, and security officials. They would debate the implications for global stability, for religion, for the economy. They would craft a careful, controlled release strategy designed to manage the public's reaction. During that period of analysis and deliberation, which could take weeks, months, or even years, the official public stance would be one of calm, cautious, even dismissive scientific inquiry. From the outside, this necessary caution looks exactly like a cover-up. The human mind, faced with silence, rushes to fill the void. People begin connecting dots that may not be connected. They point to the sudden reluctance of certain astronomers to discuss 3IATLAS in public. They mention the existence of classified space surveillance networks, like the US Space Surveillance Telescope. They wonder why certain data sets from solar observatories are not in the public archive. A conspiracy theory is born not necessarily from malice, but from the marriage of a profound mystery with a lack of transparency. The counter-conspiracy, the boring and most probable truth, is that the agencies are being as open as they can be. The gaps are mundane. The scientists are overworked, the data processing is slow, the telescopes have limited time and were not all pointed at the right place. 3IATLAS is a fascinating object, but it is one of thousands being tracked. The delay is normal science, not a cover-up, and the lack of evidence for anything artificial is simply because there is nothing artificial to find. This view is almost certainly correct. Most conspiracy theories are wrong. Most gaps have boring explanations. The problem is, history shows that sometimes the conspiracies are real. Sometimes information is withheld for national security reasons. Sometimes the boring explanation is a carefully constructed facade. Without full, immediate, and transparent access to all the data, we, the public, cannot possibly tell the difference. So, where does that leave us? We are left with a solid core of verified public facts. The trajectory shift, the timing, the keyhole precision. These are undeniable. We're also left with the undeniable reality that government agencies have capabilities we do not. Classified sensors, military satellites, data streams that are never made public. If there is a smoking gun, they would see it first. And if they see it, we may not hear about it until long after the decision makers have decided what to do. The only way through this fog is to focus on what we can verify. The 1 in 26,000 probability comes from a respected Harvard astronomer using a public NASA database. That has weight. The claim about metal alloys comes from an unnamed source in a tabloid. That is noise. In March 2026, the event itself will cut through the speculation. Juno will be there. Earth-based telescopes will be watching. If something happens, if probes deploy, the evidence will eventually surface. It may be in a grainy image, an anomalous infrared signature, a strange radio burst. It will be data, and data has a way of escaping. If nothing happens, the mothership hypothesis will be dealt a likely fatal blow. Until then, we wait in the silence, a silence that grows louder and more pregnant with possibility with each passing day. But before we become too fixated on 3IATLAS alone, we must widen our view. Because this object is not an isolated incident. It is the third in a series of interstellar visitors, and when you examine all three together, a larger, even more startling pattern begins to emerge from the darkness. To understand the full implications of 3IATLAS, we cannot view it in isolation. It is the third identified interstellar object to pass through our solar system, and when we place it alongside its predecessors, the story transforms from a mystery into a potential pattern. The sequence begins in October 2017. A telescope in Hawaii detects a faint, fast-moving object. Its trajectory is unequivocally hyperbolic. It is not from here. It is named Oumuamua, Hawaiian for scout, or messenger from afar. From the start, it is bizarre. Its light curve suggests an extreme elongated shape, like a cigar or a pancake. Estimated to be perhaps 400 meters long but only 40 meters wide, a geometry unlike any known asteroid or comet. Then, as it departs the solar system, it does something inexplicable. It accelerates, just slightly, but definitely. A non-gravitational acceleration. The natural explanation is outgassing, but Oumuamua shows no visible coma, no tail, no evidence of gas or dust. Proposals that it is a hydrogen iceberg or a nitrogen iceberg are put forward, but they are speculative and struggle to explain the lack of observed disintegration or the specific nature of the acceleration. It is Avi Loeb who, controversially, suggests the unthinkable. Perhaps Oumuamua is artificial, a light sail, a thin, reflective sheet pushed by the radiation pressure of starlight. Its shape fits, its acceleration fits, its lack of outgassing fits. The mainstream scientific community pushes back hard, accusing Loeb of sensationalism. The debate rages, but Oumuamua is gone, speeding out of the solar system, leaving behind only questions and argument. Then, in August 2019, the second visitor arrives, 2E Borisov. This one looks more familiar. It has a clear coma and a tail. Spectroscopy confirms the presence of water vapor and cyanogen. It is unmistakably a comet. A sigh of relief goes through the astronomical community. See? Interstellar objects can be normal. Borisov is the example. But even Borisov has its quirks. Its nucleus is fragile, beginning to fragment as it rounds the sun. The ratio of carbon monoxide to water in its coma is higher than in most solar system comets, suggesting it formed in a different, perhaps colder, environment. It is natural, but it is an alien kind of natural, a reminder that the chemistry of other star systems is not our own. Now we have 3IATLAS detected in 2025. It is large, several kilometers across. Unlike Oumuamua, it shows classic cometary activity. Unlike Borisov, its behavior is not just natural, but precise. Its non-gravitational acceleration was not a random push. It was a targeted course correction. It is not just passing through, it is arriving with a destination in mind. So, we're forced to ask the profound question, what if they are all related? What if Oumuamua, Borisov, and 3IATLAS are not three separate random pieces of cosmic debris, but part of a coordinated, or at least a patterned, effort? This is the interstellar gardener hypothesis. The idea is that an advanced civilization does not send one grand starship, it sows seeds. It dispatches thousands, perhaps millions, of small autonomous probes across the galaxy, each targeting a different star system. Most find nothing. Dead worlds, gas giants without interesting moons, sterile systems. These probes either self-destruct, go dormant, or continue on their way. But a few find what they are looking for. Systems with life, with activity, with potential. These probes are programmed to stay. They are the gardeners, tending the interesting plots of the galactic garden, observing, reporting, and perhaps waiting. In this scenario, Oumuamua was the first scout. It was a fast initial reconnaissance, perhaps a light sail designed for speed over stealth, taking a quick close look at the inner solar system before speeding away to report. Borisov was the next phase, a more advanced probe disguised as a natural comet, designed to blend in, to test its camouflage and to gather more detailed chemical data. And 3IATLAS is the culmination, the deployment vessel, the mothership. It is not here to look and leave, it is here to stay, to establish a permanent presence in the most strategic location available, the Jovian system. If this hypothesis is true, then our detection of 3 interstellar objects in just 8 years is not a statistical fluke, it is a sample. There may have been dozens, even hundreds of others that passed through undetected because our sky surveys were not good enough, or because they were better at hiding. We are only now developing the technology to see the traffic that has been flowing around us all along. Of course, the natural explanation exists for each one. Oumuamua's shape could be a rare but possible fractal aggregate. Its acceleration could be from hydrogen outgassing that is invisible to our instruments. Borisov's composition is simply what comets from other stars look like. 3IATLAS's precision is a 1 in 26,000 coincidence. The problem is that each of these natural explanations requires its own separate, unlikely assumption. Oumuamua's shape is rare, its acceleration without a coma is rare, Borisov's specific chemical makeup is unusual. 3IATLAS's trajectory is statistically improbable. Individually, each can be dismissed. But when you line them up, the sequence starts to look less like a series of random accidents, and more like a progression. A fast scout, a disguised observer, and now a strategic deployer. The frequency is also telling. Models based on the random ejection of comets from other stars suggest we should see a few interstellar objects per year with our current technology. We are seeing roughly that rate. But those models assume natural random processes. If the objects are artificial and targeted, the rate could be much, much higher. We could be swimming in a sea of interstellar probes, and we have only just begun to dip our toes in the water. The future will provide the answer. The Vera C. Rubin Observatory, scheduled to come online soon, will scan the entire visible sky every few nights with unprecedented depth. It is designed to find transient phenomena, and it will undoubtedly find many more interstellar visitors. If they are all strange, if they all exhibit oddities that push the boundaries of the natural, the pattern will become undeniable. If they are a mix of the ordinary and the bizarre, the mystery will deepen. But here is the ultimate chilling thought that this sequence provokes. If Oumuamua, Borisov, and 3IATLAS are probes, then someone built them, someone launched them, someone is out there, and if they have sent 3 distinct types of probes to our system in just 8 years, what else have they sent? What other, more advanced technology is already here, watching, that we are not yet capable of detecting? And most terrifying of all, what are they waiting for? Because probes do not just observe, they report, and if they are reporting, someone is, even now, listening. While our attention has been gripped by the approach of 3IATLAS, a separate quiet revolution has been unfolding in the field of exoplanet science, a discovery that subtly changes the backdrop against which this entire drama is playing out. For years, astronomers have known that exoplanets, planets orbiting other stars, are common. Thousands have been confirmed, but exomoons, moons orbiting those distant planets, have remained elusive, the ghost stories of astronomy. Theoretically, they should be everywhere, but they are too small, too faint, and too close to their bright parent planets to be easily seen until 2025. This year, a team of astronomers announced a monumental breakthrough. The first strong evidence of an exomoon with an atmosphere. The detection is still preliminary, pending confirmation and peer review, but if it holds, it is a watershed moment in our understanding of the universe. For an atmosphere to exist on a moon, it implies activity, internal heat, geological processes, outgassing. It means that moons are not just dead, frozen rocks, they can be dynamic worlds in their own right. The detection was made using the cleverest tool in the exoplanet hunter's kit, transit spectroscopy. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. By analysing that filtered light, scientists can deduce the atmosphere's composition: oxygen, methane, water vapour. The team applied this same principle to a moon. As the exomoon transited its host planet, they detected a second, even more subtle, dip in the starlight, and within that dip, the spectral signature of a thin atmosphere, likely hydrogen, escaping into space. This moon is losing its atmosphere, which means it must be actively replenishing it, most likely through volcanic or cryovolcanic activity driven by tidal heating. the constant gravitational flexing from its parent planet. Now, let us connect this back to Jupiter, because Jupiter has moons with atmospheres. Io has a tenuous shell of sulfur dioxide from its relentless volcanoes. Europa may have transient water vapor plumes erupting from its subsurface ocean. Ganymede has a thin oxygen atmosphere, likely from water ice being split by radiation. These are not habitable atmospheres for us, but they are proof that moons can be complex geologically active worlds. The discovery of an exomoon atmosphere tells us that this is not a fluke of our solar system. It is a universal phenomenon. This discovery effectively doubles or triples the number of potentially interesting dynamic worlds in the galaxy. It radically alters the Drake equation, the formula used to estimate the number of active, communicative civilizations. We are no longer just looking at planets in the habitable zone of their stars. We must now consider moons in the habitable zone of their giant planets, worlds like Europa or Enceladus, which are heated from within by tidal forces, not from without by starlight. This expands the cosmic real estate for potential life enormously, and it changes how we should think about the strategy behind 3IATLAS. If Jupiter's moons are interesting to us, with our limited technology, they would be profoundly interesting to any interstellar civilization. Europa's ocean is a potential haven for life. Ganymede's magnetic field and vast water ice are resources. Io's volcanic furnaces are a source of energy and materials. If you were deploying a surveillance network or a resource-gathering operation, the Jovian moons would not just be scenery. They would be prime real estate, the islands and continents of your new domain. The exomoon discovery also serves as a powerful lesson in detection. We found this atmosphere not by going there, but by analysing the faintest of whispers in the light from a star hundreds of light years away. We found it by inference, by looking for the signature, not the thing itself. This is how we explore the cosmos. And if we can detect a wisp of hydrogen around a distant moon, what other signatures are we missing in our own backyard? What artificial signatures might be hiding in the data we're already collecting from Jupiter, from Saturn, from the asteroid belt, waiting for someone to ask the right question? Philosophically, every discovery like this is a humbling reminder that the universe is consistently stranger and more diverse than our imaginations. Before hot Jupiters were found, we didn't think gas giants could orbit so close to their stars. Before Oumuamua, we didn't know interstellar visitors were so common. Before this exomoon, we didn't know we could detect such delicate features on such small, distant bodies. Each discovery shatters a previous assumption and forces us to widen our concept of what is possible. And if the universe is stranger, then the things visiting us might be stranger than we can currently conceive. We keep trying to fit 3IATLAS into our known categories: comet, asteroid, probe. But what if it is something else entirely? Something for which we do not yet have a name? Something that operates on principles we have not yet discovered? The exomoon atmosphere is a piece of that larger puzzle. It tells us that small worlds matter, that activity happens in the quiet, overlooked corners of star systems. It tells us that if probes are being deployed, they might not be targeting the bright, obvious planets. They might be targeting the moons, the dark, quiet places where you can hide and watch and wait for eons if necessary. When March 2026 arrives and 3IATLAS reaches Jupiter, we should not just be watching the planet or the empty space of the Hill sphere. We must train our telescopes on the moons themselves: Europa, Ganymede, Callisto, Io. Because if a deployment occurs, that is where the action will ultimately be. The probes will disperse to their assigned posts, and the moons, with their resources and their secrets, will become the most valuable pieces on the chessboard. The universe, it seems, is not only vaster than we imagine, but it's also far more crowded with interesting nooks and crannies than we ever dreamed. And we're just beginning to learn how to look. The journey between stars is a war of attrition against time and entropy. Any probe sent on such a voyage must be capable of surviving not for years, but for centuries, millennia, or longer. This presents a problem that goes far beyond sturdy hulls and reliable power sources. It strikes at the very heart of the probe's mind: its computer. How do you build a memory system that can retain its data, its programming, and its core identity for 1,000 years without degradation? Traditional silicon-based computing is hopeless for this task. Cosmic rays and other high-energy particles will steadily flip bits, corrupt memory, and degrade processors, Even with heavy shielding and redundant systems, the accumulated errors over centuries would render any complex computer brain a useless wreck. This is the error flaw, the fundamental limit of how long classical data can be stored coherently in a hostile environment. But in 2025, a breakthrough in a seemingly unrelated field provided a glimpse of a solution, a technology that could make millennia-long computational stability possible: the breaching of the quantum memory error flaw. To understand this, we must distinguish between a classical bit and a quantum bit, or qubit. A classical bit is a 1 or a 0, a switch that is either on or off. A qubit exists in a superposition, being both 1 and 0 simultaneously until it is measured. This property gives quantum computers immense potential power for certain tasks. The fatal weakness of qubits has always been their exquisite fragility. Any interaction with the environment, a stray photon, a vibration, a passing magnetic field, can cause decoherence, collapsing the superposition and destroying the quantum information. Keeping qubits coherent has required near absolute zero temperatures and near perfect isolation, and even then, coherence times were measured in microseconds. The 2025 breakthrough involved a new architecture for qubits, based on topological quantum computing. The details are complex, involving theoretical particles called anyons and braiding their world lines in spacetime. The practical result is simple and revolutionary. These topological qubits are inherently resistant to local noise and errors. The information is stored not in a single, fragile physical state, but in the global topological properties of the system. A cosmic ray striking one part of the chip does not destroy the data, because the data is not stored in that one place. The error rate plummeted by orders of magnitude, pushing coherence times from microseconds to potentially years. This means that for the first time we can conceive of a quantum memory device that could be written to, sealed, and then survive for decades or even centuries in the void of space without power, without refreshing, and without significant data corruption. The quantum state itself would remain stable, preserving the most complex instructions and the most delicate data intact. Now, let us connect this to 3IATLAS. If you're designing an interstellar probe, its computational core is its soul. It must remember its mission profile, its navigation charts, its communication protocols, and its operational software for the entire duration of its journey, which could be longer than the span of human civilization. Classical computing is a dead end for this, but a quantum memory core with its newly achieved stability is a viable solution. You could store the probe's entire consciousness in a form that is immune to the bit rot of deep time. Furthermore, quantum computers excel at the kinds of calculations required for interstellar navigation, optimizing complex trajectories, calculating gravitational assists, and processing real-time sensor data to make course corrections. A probe equipped with a quantum brain could navigate the solar system with an efficiency and precision far beyond our current capabilities. The unsettling corollary of this is timing. We have just, in 2025, stumbled upon the principles that could make such long-duration computing possible. How long ago did a more advanced civilization solve this problem? If they have been spacefaring for millions of years, their computational technology would be unimaginably advanced. Their probes could be equipped with quantum processors that are completely error-free over geological timescales, capable of autonomous operation for eons. The coincidence of our own technological breakthrough with the arrival of 3IATLAS is just that, a coincidence. But it highlights a convergent path. Any technological civilization aiming for the stars will likely discover quantum computing as a key enabling technology for long-duration missions. There is a tantalizing, though currently unreachable, possibility for detection. Quantum computations can produce specific, subtle signatures in their energy emission and noise profiles. If we could get close enough to 3IATLAS with a sufficiently sensitive instrument, we might be able to detect the faint signature of quantum processing at work. The smoking gun of an artificial and supremely advanced intelligence. But we cannot get close. It is moving too fast, and we had no warning to mount an intercept mission. Our window for close inspection is closed. The value of the quantum memory breakthrough, therefore, is not in solving the mystery of 3IATLAS, but in showing us a glimpse of our own potential future. If humanity ever wishes to send its own probes to the stars, this is the kind of technology we will need to develop. It is a technology of patience, of long-term thinking, of accepting that the grandest projects will outlive their creators by centuries. The universe is vast and ancient. The distances are cruel. But with technologies like fault-tolerant quantum memory, the void becomes navigable. Others may have already mastered it. And if they have, we are not just witnessing a comet. We are witnessing the product of a science that has conquered time itself. Navigation across the ocean requires knowledge of the currents. Navigation across the galaxy requires knowledge of a far more mysterious and pervasive medium, dark matter. For decades, dark matter has been the ghost in the cosmic machine. We know it constitutes about 85% of the matter in the universe. We see its gravitational effects holding galaxies and clusters together, but we cannot see it, touch it, or map it directly. It is the hidden skeleton of the cosmos, until 2025. This year, using a technique of breathtaking precision, astronomers used pulsar timing arrays to create the first detailed map of the dark matter distribution in our local region of the Milky Way. Pulsars are the universe's most perfect clocks. These rapidly spinning neutron stars emit beams of radio waves that sweep across space with metronomic regularity, some ticking with a stability that rivals atomic clocks. The principle behind the mapping is elegant. As the radio waves from these pulsars travel through space to Earth, their passage is subtly affected by the warping of space-time. Gravitational waves from distant cosmic events cause minute, correlated shifts in the arrival times of pulses from many pulsars. But so does the gravitational pull of dark matter. By monitoring an array of dozens of these millisecond pulses for years, and by applying sophisticated algorithms to filter out the noise, scientists have managed to tease out the specific gravitational signature of the dark matter that lies between them and us. The result is a three-dimensional map of the dark matter topography around us, its clumps, its filaments, its voids. This is a monumental achievement in fundamental physics, but its implications for interstellar travel are profound. Dark matter is not a uniform soup, it has structure, and that structure creates what are, in effect, gravitational currents and eddies throughout the galaxy. For an object travelling between stars, knowing this hidden landscape is like a sailing ship, knowing the patterns of the ocean currents and prevailing winds. A navigator who possesses a dark matter map can plot a course that takes advantage of these subtle gravitational gradients. They can ride the dark matter currents to save energy, to gain speed, or to make minute course corrections without expending propellant. Over light years, these tiny advantages compound, leading to significantly more efficient voyages. If 3IATLAS is an interstellar probe, it did not simply aim a straight line at our Sun. It would have navigated through this invisible landscape. Whoever launched it would possess detailed maps of the galactic dark matter distribution, allowing them to compute an optimal route, one that might have used dark matter filaments for gentle gravitational assists, or avoided dense clumps that would create drag. The pulsar timing array map also revealed something unexpected. The local dark matter distribution is asymmetric. It is not evenly spread around us. This means that routes into the solar system from certain directions are downhill on the dark matter gradient, while others are uphill. The specific approach vector of 3IATLAS might have been chosen because it represents the path of least resistance through this hidden terrain. There is also the factor of stealth. Travelling through a region of higher dark matter density might help to mask your own gravitational signature, making you harder to detect with gravitational wave sensors or other advanced instruments. An intelligence that has mapped the galaxy's dark skeleton would know the perfect routes for both efficiency and secrecy. We have only just drawn the first crude sketch of this map. It covers only our immediate cosmic neighbourhood. A civilization that has been exploring the galaxy for millennia would have a complete atlas, charting the dark matter flows across hundreds of thousands of light years. Their navigation would be a masterwork of precision, using every resource the galaxy offers. The fact that we are discovering this hidden architecture of space just as we are grappling with a precision interstellar object feels significant. It is another piece of the puzzle that suggests that advanced travel is not about brute force, but about subtle mastery of gravity, of quantum physics, and of the invisible scaffolding of the universe itself. In March 2026, we will see the culmination of 3IATLAS's journey. If its arrival at the Jupiter keyhole is as precise as predicted, it will be a testament not just to a good aim, but to a phenomenal understanding of a cosmos far more complex and structured than we ever knew. It will mean that someone out there has maps of the void that we are only beginning to trace with our fingertips, and they have used those maps to find us. The process of engineering has always been a human endeavour, a blend of physics, intuition, and established design principles. We build spacecraft that look like spacecraft, cylindrical modules, dish antennas, solar panel wings, because that is what we know, and that is what has worked. But what if our intuition is a cage? What if the optimal design for a deep space probe is something no human engineer would ever conceive? In 2025, the answer to that question became clear as multi-agent artificial intelligence systems began generating spacecraft designs that consistently outperformed those of their human counterparts. These AI designers are not constrained by tradition or aesthetics. They are given a set of goals: minimize mass, maximize strength, withstand specific thermal and radiation loads, and a set of physical laws. Then, they run through millions of iterations in simulation, using generative design and evolutionary algorithms. The results are often bizarre, almost organic-looking structures. A lopsided thruster cluster here, a strangely curving support strut there, a heat shield with an irregular, non-symmetrical pattern of grooves. To a human, they look wrong, inefficient, even clumsy. But in simulation, and in subsequent physical testing, these AI-generated designs prove to be 20% lighter, 15% more fuel efficient, and significantly more robust than the best human-designed equivalents. They find optimal solutions in a vast design space that human brains, with their inherent biases towards symmetry and simplicity, cannot effectively explore. This has profound implications for the search for extraterrestrial intelligence and for the mystery of 3IATLAS. In our imagination, an alien spacecraft is often sleek, metallic, and geometrically perfect. But what if it is not? What if the most efficient design for an interstellar probe, as determined by a superior alien AI, is one that is irregular, lumpy, and non-reflective? What if it looks, for all intents and purposes, exactly like a comet? This is the ultimate camouflage. 3IATLAS's cometary appearance, its outgassing, its irregular shape, its dark surface, could be its true engineering specification, not a disguise laid over a more conventional structure. The optimal interstellar probe might be a comet, because looking and behaving like a common piece of cosmic debris is the most efficient way to travel undetected through a solar system. The AI design revolution also suggests a kind of technological convergence. Different AI systems on Earth, given the same physics and the same problems, often arrive at similar non-intuitive design solutions. Physics is physics, and optimal solutions are optimal, regardless of the mind that finds them. It is therefore plausible that an alien AI, tasked with designing a long-duration interstellar probe, would arrive at a solution that looks remarkably similar to what a human AI would design. The mothership might not look alien to us in principle. Its logic might be recognizable once we understand the constraints. The frightening side of this is the black box problem. We often do not fully understand why an AI's design works so well. The logic is embedded in layers of neural network calculus that are difficult to translate into human engineering principles. If we were to recover an alien probe designed by a vastly more advanced AI, we might not be able to reverse engineer it. Its very structure, its material composition, its power systems might be so optimized and so foreign to our way of thinking that it would be as incomprehensible as a smartphone to a medieval knight. This is the challenge we face with 3IATLAS. Even if we were to get a sample, to scan it with our best instruments, we might not understand what we're seeing. Its brilliance might be hidden in its optimal, and to us, bizarre, design. The progression is clear. Our own AIs are already surpassing us in specific design tasks. A civilization that has had AI for thousands of years would have optimized everything to a degree we cannot fathom. Their probes would be perfect, durable, efficient, and stealthy beyond our current ability to conceive or detect. 3IATLAS could be the product of such a process. A design so perfect, we're forced to explain it away as a natural object. It is the ultimate stealth, hiding in plain sight, not by being featureless, but by being a perfect imitation of the commonplace. The final piece of the 2025 puzzle comes from the very edge of our solar system, from the boundary where the sun's influence ends and the true interstellar void begins. The heliosphere, the giant bubble of solar wind that encapsulates all the planets, is our first and last line of defense against the galaxy. It shields us from the majority of galactic cosmic rays and defines the territory of the Sun. In 2025, data from the Voyager probes, the IBEX mission, and the upcoming IMAP mission revealed something unexpected and dynamic. The heliosphere is shrinking, and its shape is changing faster than our models predicted. The leading theory is that the local interstellar medium, the cloud of gas and dust through which our solar system is moving, is denser than we thought. This denser medium exerts a stronger pressure on the solar wind, compressing the bubble. The heliosphere is becoming asymmetrical, bulging in the direction of travel and compressed in the tail. This matters for two crucial reasons. First, a smaller heliosphere means less shielding from cosmic rays, with potential impacts on climate and astronaut safety. Second, and more relevant to our mystery, it changes the entry conditions for interstellar objects. The boundary layer, the heliopause, is now closer and weaker in certain directions. An object approaching from interstellar space could target these soft spots. It could slip through the heliosphere with less deceleration, less deflection, and a clearer, more energy-efficient path inward. Let us consider the trajectory of 3IATLAS. While we do not know its exact entry point, its approach vector is consistent with it coming from a direction roughly aligned with the tail of the heliosphere, precisely the region that is now known to be more compressed and potentially weaker. This is not proof, but it is another point of alignment. If you were navigating a probe into a new solar system, you would use your knowledge of its heliosphere to choose the easiest entry point. You would aim for the path of least resistance. The changing heliosphere also provides a natural cloak. The heliopause is a turbulent region, emitting its own radio noise from the collision of solar and interstellar wind. An object crossing during a period of high turbulence or through a weak spot could mask any minor emissions or thermal signatures it might have. It is another form of environmental stealth. We are only beginning to understand the dynamics of our own heliosphere. The Voyagers provided 2 data points. We are trying to map a vast dynamic structure with a handful of sensors. An advanced civilization would have mapped the heliospheres of thousands of stars. They would know their typical structures, their cycles, their vulnerabilities. The 2025 heliosphere data completes the picture. We have an object exhibiting intelligent behavior, the hidden maneuver, heading for a strategic target, Jupiter's keyhole, using what could be advanced propulsion and computation, designed for optimal stealth, and arriving at a time when our own solar system's defenses are in a state of flux, potentially easing its entry. Every thread of discovery from this remarkable year seems to weave into the same tapestry. March 16th, 2026 is the date. The destination is Jupiter's Hill Sphere. The event is the passage of 3IATLAS through the keyhole. The question is what happens next? If the mothership hypothesis is correct, this is the moment of deployment. It is the moment we learn that the solar system is not ours alone. If it is incorrect, it will be the most spectacular anticlimax in scientific history, but one that leaves behind a residue of unnerving, unanswered questions. The instruments are poised, Juno is in place, telescopes around the world will be watching, the data will flow in, and when it does, we will have an answer. We will know if the Jupiter system is empty, or if we have neighbours. We will know if 3IATLAS was a rock or a messenger. We will know if the universe is indifferent, or if it has been watching us all along. The countdown has begun. The story of 3IATLAS is a story about evidence, about probability, and about the courage to follow the data wherever it leads. It is a story that will be written in the cold, hard numbers of orbital mechanics and the silent digital packets of data from a probe named Juno. And when the final number is crunched, when the last image is analysed, our world will either be the same as it always was, or it will be utterly, irrevocably transformed. Watch the sky. Watch the data. Prepare for the answer.